Hello and welcome to the next session of the Real-Time Systems Development module. What I intend to do today with you is to review everything we've learned up to now. We're going to add in a few new concepts, that's serial communication techniques and networking in real-time systems, and then that will draw a line on the fundamental basics of the module. Later on we'll move on to some more software orientated concepts, but today I hope to finish everything to do with the hardware, the electronics and the external interfacing. Now before we go on any further, let's review our overall concept that we're interested in. A real-time systems job is to monitor events in the outside world where we live. How do we do that? Well, we extract out of the real world measurands. Measurands are things we want to measure in the real world: pressure, temperature, volume. We've been through this before. Somehow or other, we are trying to get that into our microcomputer. How? Well, we've looked at the various tools to do that. Starting point is transducers. Most important, transducers. These are components that will convert one form of measurand into another form of measurand. For example, as we'll look at later, here we have the pressure cell where air forces into the pipe, distorts the metal, and we get a capacitive effect that then gives us an electrical signal we can monitor. So what is a transducer? A device that converts one measurand into another measurand, ultimately with the view of getting out an electrical signal. Why electrical? Because we need to get this information into our computing system. And there are a variety of tools we can use to convert the electrical signals into numbers that the microcomputer can use. So, rules about transducers: they convert one measurand into another measurand with a known mathematical relationship. That's the key, because ultimately when we get our number 375.2, whatever it is, what does that mean? That has to be related back to a real thing, a real event, a real measurand in the real world. So we must know the precise mathematical relationship between all of these interfacing devices so we can relate that number back to the real engineering value in the real world. Now, there are a family of very interesting devices that combine together the concept of a transducer and an electrical signal. This family of devices are known as transmitters. Transmitters. Now, you've probably heard the word transmitter before with reference to, say, local area networks, RS-232, serial communications devices. In the world of real-time systems, the word transmitter has a special meaning. It's these sort of devices. It's a device where the transducer itself is connected directly to the computer by a set of wires. So a transmitter is a special class of transducer that combines both the transducer with the mechanism to transmit the information from the remote environment to the computer. Why do you want to do that? Well, this is a very high pressure sensor. It could be measuring the pressure of a hot oil pipe in a factory in a very harsh environment. Your computer wouldn't survive in that environment. So what you want to do is to put this very robust lump of metal, the transducer, in the harsh environment while you run away to your nice, clean, air-conditioned room where you have your computer. And what you want to do is to have something that will transmit the signals directly from the transmitter to your computer. Let's just run through the types of transmitter you might come across. Transmitters are classified into three different types. I have shown you a 4-wire transmitter. Here we have, coming out of our transmitter, we have 4 separate wires. Why is that? two of the wires, the red and the blue in this case, these two wires, these are the power supply that power everything that's required inside the unit, both to operate and to transmit. And the other two wires, these are the transmission loop that sends the data back to our computer. So if we look at a picture of a 4-wire transmitter, two of the wires are the power supply, PSU, power supply unit, typically plus 12 volts or plus 24 volts. More commonly it's 24 volts. 24 volts is a very common power supply voltage to use for process plant and factory automation. The other two wires, these two wires are the transmission loop. Now transmission only occurs in one direction, from the transmitter to the microcomputer. So over here we have our microcontroller, our microcomputer that reads the information back. Here is the 4-wire transmitter, our 4 wires. The other signal is a 0-volt reference that the transmitted data is referenced to, so that we have the ability to have an independent transmission loop, totally independent of the power supply. Now that's done for very noisy environments. If you have a very noisy environment with a lot of electrical interference, the voltages that are modulated down the actual power supply can be quite corrupt. You have to smooth them out to drive your electronics, and so you want to keep these very nasty unsmooth voltages and signals away from the transmission line. So they need to be independent in noisy environments. So let's look at our picture now. We have our transmitter, our power supply, and our signal. Now, one thing that you may not occur to you, what is the most expensive part of any factory? And it's not the computer, it's not the plant equipment. The most expensive part of any factory is the ongoing costs over 25 years of maintaining it and keeping it working. That costs far more than you will ever spend on the buildings, the factory, the staffing. It's the maintenance costs. A lot of companies go out of business because they forget about the cost of maintenance. And the one thing that is most likely to fail in any system, in any computer, any network, it's not the computer, it's not the transducers, it's the wiring. Because these are laid around all around the factory. Idiots will come along with power drills and cut into them. People will pull them and break them. They will just wear over periods of time. People forget where they've laid them. And how do you lay them in? You have to lay in expensive trunking. You have to package them. You have to seal them up. You have to drill holes in walls. Wiring and cabling is a major expense in any factory. The more you reduce your wires, the lower the cost of the maintenance will be. And it's often worthwhile spending more money on the initial components to have fewer wires than it is to have the cost of the maintenance of the wiring that goes around the factory. So let's go back to our picture of our 4-wire transmitter. Do you think there's anything here we could do to improve the situation? Well, one thing that was realized actually in the 1950s, is an old idea. If we have a power supply here, why don't we reference our transmission signal to the negative side of the power supply? Get rid of that 0-volt return and combine the two together into one. So we have our power supply and we have our transmitted signal, whatever it is, relative to the negative power supply. And what we have now created, instead of a 4-wire transmitter, by combining together our return and our 0-volt signal into one, we can just twist those together. That now becomes a single wire, a 0-volt for our power and a return signal for our transmission. We have a 3-wire transmitter. Why? Because we've reduced by 25% the amount of wiring and cabling you need in your factory, and that will save you a substantial amount of money over the years. So let's look at our picture. We now have a 3-wire transmitter we have our positive supply, typically 24 volts, a common 0 volts, and a transmission signal modulated out that sends the information back to our remote system. But can we go further? Are there any improvements on this? Well, in fact there are. And modern transmitter technology now combines not just the 0 volts together, that was the easy trick. They combine the power supply with the transmitted signal. What they actually do is they modulate back on the power supply the information from the remote transmitter. And thus we had born, in fact they've been around for about 20 years, you're just about beginning to see them in the home, the 2-wire transmitter concept. Let me draw that for you and we'll see how that works. So a 2-wire transmitter we have a single 0 volt reference and we have a single transmission wire, but that combines together supplying the power to our system, and modulated on top of it back again is the transmitted information back to the remote computer. So by this mechanism, we'll look at this in a little bit more detail shortly, but by this mechanism we have halved the wiring in the factory. And I can assure you that has resulted in substantial savings in both factory design, factory costs and maintenance of factories by going from the 4-wire system to the 2-wire. Because even though you might think the key of everything is a computer, it's not. If you actually think what's in a factory, you're going to have dotted all around it machine tools, presses, forming machines, moulding machines, ovens, and somewhere in the middle there'll be a central control unit. Each of those pieces of capital equipment cost money, but think of the size of a standard factory. There are miles and miles of cabling all around the factory connecting those pieces of kit together. And halving the amount of wires from 4 to 2 was a major breakthrough. And as we will see in a much later lecture, there's even been more advances in the networking technology that you will find in a standard factory. But let's just briefly look at one way this is done. Now, the way it's normally done is that rather than modulating voltage, we modulate the current on the system. And the way it works if this is our 2-wire transmitter with a common 0 volt supply, the power supply is usually 24 volts. That is a standard factory power supply. Thus, that's why we've had to cover things like relays, which are used to switch 24 volt supplies using just a volt computer signal. This is quite an important concept because most factories are wired up with 24 volts, not 5 volts. And 5 volts is the computer level, whereas 24 volts is a factory level and also what's used in cars. So how do we modulate information on the 20 volts? If that is a fixed voltage, the way it's done is by the amount of current that is drawn. The current is a measure of the amount of power you're draining from the remote source. The 24 volt supply is just a dirty great big battery that is stored remotely in your control room, providing a 24 volt signal. What you vary is how much power you drag out of a battery. Now, if you've not done this concept before, it's not essential for you to understand the physics. I certainly won't examine you on the actual physics or electronics of what's going on, but I want you to be familiar with the terms. As you must know, if you have a battery, if you can either draw a little bit of power from it, or you can draw a lot of power. The more power you draw from it, the brighter the lamp is, the faster the motor goes. But also, that is measured by the amount of current, that's the electrical term, that you draw out the battery. And as you draw it out, so it flattens. How do we use this concept in a transmitter? Well, all transmitters use 4 milliamps of power as standard. 4 milliamps. It's minuscule and it's nothing. It's a very small amount of power. That is the bare minimum required to power the whole of the electronics and the transmitter system. Now all this has only become possible because of the low power electronics and sensor systems that have appeared in the last few, actually decades I should say, but it's recent history in terms of factories. 4 milliamps is nothing. You can run it off a little small battery, and that is all you need to power transmitters like that. The way it modulates the data is that it has the ability, if we think of 4 milliamps, 0 to 4 milliamps, that is just the power to drive the unit. But in fact, we're able to draw up to a maximum of 20 milliamps, if we so wish, from the remote battery. And what we do is that in this area here, we modulate the transmitted information in the top of the band. So what I have introduced to you we just draw a graph of what happens in real time, is what is known as the 4 to 20 milliamp transmitter. There is always 4 milliamps drawn from the remote battery to power the remote system. But the actual signal we want to transmit back is achieved by modulating that information in the remaining area, the 4 to 20 milliamp band on the transmission system. Now traditionally this was done in an analog manner, which meant that 4 milliamps equals 0. 20 milliamps would equal full scale. Halfway between the two, what's that? That's 12 milliamps. That would be half full, and it's as simple as that. So if you measured back at the computer how much current being drawn out of the battery, if you just measure what's being drawn out by the remote transducer, so here's our transmitter a long way away, if it's only drawing 4 milliamps, it means we're at 0. If it's pulling 12 milliamps, it means it's halfway. If it was pulling 20 milliamps, that was full scale. So thus the amount of current that is drawn by the remote transmitter is directly proportional to the variable, the measurand we are trying to sense. That is the traditional analog two-wire system. But of course, with modern techniques, we'll have digital signals. If we treat that as a logic level 0 and that as a logic level 1, we have the ability now to transmit binary data in the current loop area, transmitting data back to the remote system digitally if we so wish. Let's just have a brief review of transmitters. Transmitters are special classes of transducers that have wires dangling out the back. So you have the ability both to measure and to transmit data. Traditionally, this is quite an old one, that's why I've got it. It was given to me as a free sample. They had 4 wires, 2 wires for the power and 2 wires for the transmitted signal. But to reduce the amount of wiring, if you combine together the 0 volts of the signal and the 0 volts of the power, you have a 3-wire transmitter. And these are still quite widely used. But the really clever devices are the ones that combine together both the signal and the transmitted information onto a single wire. You draw out of there a fixed amount of power to power your unit, and you modulate on the remainder of the available power range the signal you want to transmit back to the remote computer. So let's return back to our picture that we're going to build on. The world, measurands, transducers and transmitters produce electrical signals that we convert via ADCs into numbers, or we have to use timing techniques to measure frequencies. Our ADCs, flash, successive approximation, dual slope and sigma delta, all of them are different ways of achieving a number. What about timing? Just a quick review about how do we achieve that? What do I mean by timing? Well, the other alternative output of a transducer could be either a level or a pulse train. If it's a pulse train, that's the most common. How do we measure the frequency of that pulse train? Well, let's look again at the contents of a standard computer, standard microcomputer, all of them must have something that does some sums, an arithmetic and logic unit, some code space, data space. These are standard. The other thing I've said that they always have I/O. That means that on the actual pins of the processor itself, there are memory mapped digital inputs that go straight into the memory of the processor. So I can take any of these boards I like that we've seen in the past, I can put down, and I can with quite clear honesty say, of these 40 pins on this device, 32 of them on this particular device are memory mapped I/O. These particular pins go straight into the memory map in the data space of the processor, and that means that if that's a pin on the device, that is memory mapped into there, and if our program, which is stored in the code, has a pointer that points to that memory map I/O, we can read the state of an output signal directly. Now that means that reading a level is very easy, because all our program has to do is point to that pin and say, you know, if that memory location is high, it's on, if it's low, it's off. That's easy. What about timing? What about frequency measurement? That's a different story. Now remember, our device has a crystal. That crystal is divided down by a prescaler to give us the basic clock within the computer system. That would then go through some form of programmable divider, which you have to put your value into it. This divider is always available for you to write any number you like into it under program control, so you can dynamically change it during the lifetime of your function in case you go faster or slower. It's quite a powerful technique. The output of that will be some time reference of your own choice. That will then go into what is known as the FRC, the free running counter. All microcontrollers have a free running counter. If they don't have them, you can't use them for real-time work. If you don't have a clock, how can you do real-time work? You must have a programmable clock in your computer to do this sort of work. And all microcontrollers have a free running counter within it that you can read at any time under program control, so you can know the current time and you can schedule your processes. So how does this free counter work? Well, normally it's a 16-bit device, and it just counts up until it overflows. And when it overflows, it goes from FFFF back to 0000. Now, how can we use this thing to measure frequencies? Here's our input frequency. What is an input frequency? Well, the input frequency is the time. If that's T0 and T1, then the frequency is given as the inverse of T1 minus T0. Simple bit of mathematics. But we need to know what times these occur. There are various techniques to do this, lots of different techniques, and in fact part of your coursework is to examine the different techniques and give me solutions, your preferred solution for the particular problem I've set you in the coursework. I'll run through some of them. Think of the structure of our basic computer. Going back to our previous picture, I've said I/O pins are always memory mapped. So we could have a very simple program that just runs around in a very, very tight loop, looking and monitoring that pin. When that pin goes from low to high, say I'm off, I'm now on, look at me, your program will detect that, and it can then run off to the free running counter and say, right, what's the time now? Take a copy of that time into a local variable and then wait for the next high transition. So we read T0, then T1, reading the time 0 and time 1 from the two counters, take the difference, invert it, we have the frequency. That technique is known as polling. Polling. Why is it polling? Because you're polling, looking regularly at the input signal, and when you see it go from low to high, you take a copy of the time. The difference between the two times is a measure of the frequency. Very simple mechanism. What's the problem with that? Well, if you're busy doing lots and lots of other things, if you've got to service a printer and a keyboard or some output device, instead of having a tight loop polling all the time, you might have to go off and do other things. That could delay you. That could delay the time it takes you to respond to the event and do something about it. So that's where we have to introduce the concept of interrupts. And we're going to do a major session on interrupts at a later date. What is an interrupt? Spelt wrongly there, don't worry about it. An interrupt is an external event that says to the processor, stop! I'm very important. Forget what you're doing now, stop every other program and just look at me, service me. I am the most important. So where would you use it? Well, obviously timing things are very important if you want to get the exact time. It could be the brake pedal of your car. Now, when I press the brake pedal of my car, I want that brake pedal to issue an interrupt to the engine management system of the car to start servicing everything needed to do to slow the car down. That's an interrupt. There are other examples you can think of. But an interrupt system gives you the ability to take a better snapshot. So the way that works, going back to our picture here, we've talked about polling. The alternative is, if that input signal goes to an interrupt pin, that will then call an interrupt service routine, which is a program. And what our program does here is it takes a copy of the current timer, and that number now we know was near instantaneous. The rising edge there issues an interrupt to the interrupt service routine. Everything else is stopped. And we immediately read the timer and we store it for later processing. That is an interrupt approach to the system. But as we'll see later on, if you've got multiple interrupts running, you could have problems with that concept. Because if an interrupt is already being serviced, you can't stop an interrupt to service another interrupt. You must finish the interrupt itself. So, what I've introduced to you instead to overcome this problem is the idea of, if there's our free running counter, is the input capture register. And what the input capture register is it combines the idea of a free running counter with an interrupt. It still issues an interrupt. When the interrupt occurs, a signal is sent to your processor to say stop what you're doing and service me. But it also takes an instantaneous copy of the time that the interrupt arrived. And that means that even if you're delayed in executing your interrupt routine, you can always go back to the copy that was taken. It's like having a log. The interrupt occurs, the time it occurs is written for you into another memory location. When you finally service your interrupt, you can go back to that memory location and you can see what time it occurred. So what happens is, on the rising edge of our signal that goes into our interrupt pin, that issues a call to our interrupt service routine as before, but also instantaneously a copy of the free running counter is copied into the input capture register. And now our interrupt service routine, when it is finally called, just in case it's delayed, instead of using the free running counter, because of course that's clicking on, and the time you'll read from there isn't the time the event occurred, it's the time you actually finally got round to doing something about it, and there could be a delay. However, if instead you read the contents of the input capture register, then you will have the true time that the input event occurred. So that's three ways of measuring frequency inputs. What about outputs? Just very briefly, I'll have to cover now the concept of an output capture register. Output capture is used for a different purpose. Input capture captures input frequencies. Output capture is a way of predicting, trying to give you an interrupt sometime in the future. Why would you want to do that? Well, if you want to generate an output frequency, what you have to do is to drive the signal high in your program and then sometime later drive it low again. How can we do that? Well, there's various ways to do it. The simplest way is a simple program loop. All we do is that we have a program loop. We know that 30 times around the loop is so many milliseconds, and so we can use the program processor time itself to generate the output frequency. There's nothing wrong with that, and it's very widely done. Basic program timing can give you a very good time reference. The other way to do it, which might be a little bit better, let's not forget, we have here the free running counter. That is memory mapped, so we can view that at any time to see what the time of day is. So now we can use a polling technique. If we know that at such a time of day we have to take our signal low, every now and again we keep looking at the free running counter. When we see it reaches that time, and remember, use a greater than or equal to, because you want to be equal to or past it, then you take the signal low, so you can poll. Another way to do it is to use instead the output capture technique. What you do is, in the output capture, is you copy into it the current contents of the free running counter, that is the time now, plus the interval that you want to wait. So that's this time period there. And what we do is we have in here effectively an alarm clock. What we've done is we've taken the current time, we've said we want to wait so long after that current time and then do something. We write it into the output capture register. This will now start clicking on. When the free running counter reaches the output capture time, remember we've got the free running counter time now, we take a copy of it now, we add to it our interval, and we go away. Our free running counter keeps on clicking on and on and on because it's a time reference. When they match, that issues another interrupt. And so when these two equal, when the FRC equals the output capture, we issue a request for an interrupt service routine, and that routine is the one that we will use to toggle our signal low. So that's how we can do output frequencies. So I've given you three different methods of measuring input frequency, three different methods of measuring the output frequency, and you can use whichever one is the most appropriate for your task. Welcome back. So we've been talking about the structure around the microcomputer, how your computer or your controller, I use the terms loosely, that they are the same thing. Some people call them microcomputers, some people call them microcontrollers. I think controller is a better term because it tells you what you're finally doing with it. We have around our microcontroller a variety of peripheral devices. Let's just look at the structures we have. There's our basic microcontroller with the arithmetic and logic unit to do our maths, our code, data, I/O, digital I/O, that's all memory mapped, and these timing elements that I've been referring to. But we're having to add around it some other devices. Now ideally you want to get everything into that one device. There's an example. Very, very small real-time device, and everything is in there. Virtually everything. There's a little bit of output there, which are some LEDs, but the whole of the computer is just in there. And you can get some idea of the size of it. I have here a small coin, and there's a small coin, and the whole of that black blob you can see next to the coin, that is the whole of the microcomputer. Very, very tiny. Very important to try and get things as small as possible. Here's its batteries. The batteries are bigger than the computer. And here's some input and output devices. Nice, small, compact. Ideally, that's what you want. More than anything, you want to get everything compacted into a single device. Unfortunately, you don't always get it. Now, there are devices these days, this one in particular, the actual ADC is actually on the chip. You get pulse width modulation drivers on the chip. You get a whole host of very exciting devices built into modern microcontrollers to give you these very small packages. But you don't always get it. We've already discussed you may have to have externally and ADC. We've discussed other ways to expand the system. You may not have enough I/O, so you may have to have added on one of these 8255 devices that's perhaps scanning an external matrix keyboard. There may be enough timer devices there, so you may have to have added on this 8253 timer device to give you extra timing facilities. So we're building up the actual device. Now, traditionally, what do these devices look like? The way they used to work, because they grew out of computer technology rather than controller technology, traditionally these devices sat on the bus of the computer. Now, you should have covered computer architecture elsewhere. I'm not going to review it. All computers have an address bus and a data bus where you snake wires around the system. You can actually look at it on one of these cards. If I can find a suitable card with a nice bus, we'll have a look at the bus. In fact, we'll just turn this one over. Here we have, looking on here underneath at the circuitry, we have the actual computer itself is sitting there. That's just on the other side, and we have here these parallel lines here. These are part of the bus. And over here, the horizontal lines, we have the bus there. Because of course, when you lay out a printed circuit board, you do the horizontal lines on one side and the vertical lines on the other, using the vias to connect the two. So here we have the fully expanded bus. What we've had to do with that is to bring out onto this computer the whole of the address and data bus. That's so we can interface these bus-orientated devices. Now, what we would do in our basic computer design, there's our microcomputer with all its internal functions, but we would have to bring out of it normally a 16-bit address bus and an 8-bit data bus. So there's the address and there is the data. And what we would do is have some form of memory decoding, and we would have all our peripheral devices sitting on them. So the address bus and the data bus has to go to every device that's sitting within our system. This could be our ADCs, our timers, our I/O, everything is here. Each device is given a unique address in the memory map, and then it communicates backwards and forwards via the 8-bit data bus. That is the standard traditional computer structure. Bus orientated. The problem with bus orientated systems is you end up with enormous processor cards like this. So even though we might have started with a nice compact microcomputer in the middle, we've had to expand it all out into a far larger system, a far larger board. There's the microcontroller. Everything we had hoped we would need is on there, but we've had to expand it all out onto a far larger board. Now, that's not the way things are going these days. We want to make things small, compact, tiny, like this. So we need to move away from the parallel bus structure to something more compact, and that's what we're going to talk about now. And what I'm going to talk to you now about are the variety of single wire and small wire techniques to provide serial communications between chips on boards. That's the solution. And what are we doing? We're replacing 24 wires, the 16-bit address bus and the 8-bit data bus, with 1, 2 or 3 wires depending upon which standard we adopt, and we use a serial communications technique. Not to talk over long distances. You've heard of serial communications, for example RS-232 terminals to modems over distances. These are the serial communication techniques that are used to allow chips to communicate with each other on tightly integrated circuit cards. And then we're going to talk about 3 different standards. I'm going to talk about IIC, inter-integrated circuit, sometimes referred to as I2C. We're going to talk about SPI, serial peripheral interface, and we're also going to talk about the touch memory standard, newly launched onto the market, becoming very, very popular. And that, in fact, allows ICs to communicate with each other over a single wire only. That's a single wire technique. That uses 3 wires, and that uses 2 wires. And it is your job as the programmer to write the transmission and reception software that will handle these particular communication standards. So we need to go through them. And you've got to set a note on these. It's section 4 of the notes, serial communication systems techniques. Let's take them each in turn. SPI, serial peripheral interface, is a very widely adopted standard by many different chip manufacturers. It is a 3-wire standard, which means it's full duplex. 1 wire is the clock, 1 wire is the transmit data, and 1 wire is the receive data. Now let's look at how it works. It's used to interface 2 integrated circuits together that are bonded onto the same board. One of the wires will be the clock. One of the devices is designated the master, usually our microcomputer. So it generates the clock, and it has a SDO, serial data out wire. And our remote unit could be anything, an ADC, some I/O, timer, whatever it is you have externally. There are dozens of different components you can now buy that you can bond onto your microcontroller using these techniques to expand its internal capability. It always talks back to us along the serial data in wire, SDI. So we have a 3-wire technique. These are the key things. 3 wires. It's full duplex. Why? Because both the master can talk to the slave and the slave can talk to the master simultaneously, because there's 2 wires. But the clock is always generated by the master. Now let's look in more detail at the software structures that make it work. Just considering the serial clock and the serial data out. The clock is generated by the master. And the rules are that on the falling edge of the clock, the data must be stable. So if we do a data diagram, you may not have come across these before, but this is the way they're normally drawn. What this symbol means is that while it's in the midpoint, we don't care what the value is. At this point, it must be either a 0 or a 1. It must be a fixed value. And it has to be fixed for a certain period of time before the event and for a certain period of time after the event. So this defines a serial transmission line. While the clock has gone low and is changing state, we can output another bit. The rule is that on the falling edge it must have stabilized to a 1 or a 0. Now we can change it, output our new data signal, take the clock low. So here we have the ability to transmit 3 bits. As the clock is low and rising, we can change our state. On the falling edge, the data must be stable. So it's the falling edge that is used to clock the data. Using this mechanism then, the master will clock out data from itself to the other end of the system. Now simultaneously, we will be transmitting data back from the slave into the master. So here is the serial data in line, and on the falling edge of that clock, that data line, the input line, is sampled, and so we will read the result back. So at the same time as we clock out a bit, we clock one of the data bits back into our microcomputer. So we have here the mechanism to transmit backwards and forwards binary data from the master to the slave, and from the slave back to the master in a full duplex manner on the falling edge of the clock. So the basic standard is we have a clock generated by the master. On the falling edge of the clock, the data must be valid. So when the clock falls, one bit of data goes either direction. The serial data out line transmits a single bit out, and the serial data in, you receive a bit and you need to put it into a holding register in your software. Unfortunately, some other manufacturers have decided to do it the other way up. So be very careful. You may come across SPI standards where in fact it's the rising edge of the clock that the data is clocked in, and the only way you can be sure is by reading the data sheets. Now most manufacturers are now standardizing around the falling edge technique, but unfortunately there are some others that are still using the rising edge as the point where the data is deemed to be valid, on the rising edge. So just be warned, you must read the data sheet, you must make sure you have agreed the direction of the clock. But because you're generating the clock using a computer, you can drive it any way you like. You've got to write the program to make it operate correctly. So what I've shown you is how we output bits from one end to the other. Data is also packaged up to be useful, and it's packaged up in bytes. Commands and responses are always byte orientated. So in order to output a command, we have to output 8 bits of data, and it's done most significant bit first. So we do bit 7, 6, 5, 4, 3, 2, 1 and 0 in that order. We clock out 8 bits of data using the bit clocking technique you've just seen, and we always clock out most significant bit first, and it's always in a byte. Now at the same time we will be receiving back 7, 6, 5, 4, 3, 2, 1, 0, a byte from the slave device on the serial data in line. So we've got data going out and data coming in simultaneously. It's always transferred as 8 bits in a byte, and it's always most significant bit first. So it's a very simple structure. A clock, data out, you clock a byte at a time, and data in, you receive a byte at a time. Full duplex. Think of the software implications of this. If you've just started the transmission, so let's go back to this picture. Here's the first byte we output on serial data out. What is this data coming back from the slave? Well, it's rubbish. It has to be rubbish, because the slave has never received a command. How does it know what it's supposed to send back? Something will come back, but it's garbage. The problem is, even though it's full duplex, in a master-slave environment, you have to output a command before you can get the correct response back. And this means that the replies from the slave are always out of phase by 1 byte transmission. Has to be, because how else does the slave know what to do? So on a typical transfer, we would output a command and we would receive back garbage. On the next transmission, we'd output command number 2. But what comes back is the reply to the previous command from the previous byte. Remember, these are the byte operations. Byte 1, byte 2, byte 3, and the slave is always out of phase. It gets the command on the first transmission, then it sends its reply back on the next transmission. So if we send out a command saying, send me the lower byte of the result of the ADC, it would come back then, in the next time frame. That command could be, send me the second byte of the ADC result. That's going to come back on the third clock period or byte period. But for that to happen, we have to clock out something else. So in fact, we also always need a no operation command simply to provide the clock space to get back the second reply. That is because everything's always out of phase. Clock out a command, you get the reply back on the next byte cycle. Clock out a next command, then you get the reply. But in order to get this reply, something else has got to be clocked out. So you have to clock out some garbage. So there's some redundancy in this concept. If you've got a lot of data to transmit, then it becomes reasonably efficient. But if it's very small patchy bits of data, because of all this redundancy, the fact that the first command, there's always garbage back, and then we have to clock out in some form of no operation just to get the final reply back, then you have redundancy in the system, wasted bandwidth. Now the obvious solution to this is to do your program in a loop. Try and get your program running around in a nice loop. So example, an ADC. ADC, there would be 3 commands. One of them would be start converting. Then it would be send me back the lower byte of the result, send me back the higher byte of the result. If you then loop around and you clock out the next command to say reconvert, you could receive back in that time frame then the rest of the result. So we could have something very cyclical that's quite efficient. Looking at it in time, we could say start conversion, but what will come back, if here is serial data out, serial data in, that's garbage. Then we could say send 1. That would still be garbage. Then we could say send 2, the second byte. Now we would get back reply to 1 from there. Now we can start the next conversion. And what would we get back? We would get back here the second part of the reply. So what we've done is we've made use of this redundancy period. We've interleaved these 2 operations to get rid of one of the redundancy periods so we get back the last part of our result when we start off the next cycle. So if we have a program loop that's a nice tight loop, we can get rid of this redundancy. So SPI, full duplex, 3 wires, a master and a slave. The master generates a clock, it clocks out data on the serial data out line, it receives data back on the serial data in line, and normally, here's the basic picture, this usually happens on the falling edge. That's when the data must be valid, but be wary of some systems do it on the rising edge. Data is always transferred in bytes. most significant bit first, bit 7 to bit 0. And don't forget, they're always out of phase with each other. There will be some redundancy. So, because there was always this inbuilt redundancy, the technology moved on. They said, look, why are we bothering to have 3 wires? If we're always having to wait for the result to come back anyway, why don't we go over to a full half duplex system using a clock and a single transmission wire? Why don't we drive it in both directions? So what we do is we'll clock out the signal, the command, and then we clock back in the reply. Why do that? Because now we can have a 2-wire system and we reduce the amount of copper tracks we need to lay down on our printed circuit boards. And that is the I2C, or the Inter-Integrated Circuit Standard. I2C, Inter-Integrated Circuit. And the way that it works is that we have a single clock line that comes out of the master into the slave device, and a single serial data SDA line that is bidirectional. Either of them can transmit from master to slave or slave to master, but now that is a half duplex standard. They can't both talk at the same time. No, it's like the telephone. You can't both talk at the same time. If you both talk at the same time, nobody will hear anything. You've got to take it in turns. So the master transmits out data, a command, and the slave then sends the result back in a master-slave relationship, half duplex. Now that was one of the step forwards that was done. Now the other step forward that was added to the standard was some form of synchronization, frame synchronization. SPI relies on clocks. If there was a bit of noise that perturbed that clock, the bits could get out of phase with each other, and rather than transferring data in a nice loop, nobody understands what's going on because the actual data is corrupted. What you need to do is to resynchronize that character position at regular intervals. That is achieved in the I2C standard by a mechanism that frames the data transfer. And you've got some pictures of this in your notes. If you turn, it'd be useful if you turn to this page in your notes with these pictures on, and then I will take you through what these particular pictures mean. So just take a few moments just to get to that page. And while you're getting to that page, I'll run you through the basic concepts again. I2C, Inter-Integrated Circuit. I2C. Master device, slave device, clock. Clock's always generated by the master, and the full duplex serial data. Now, what this standard defines, it says that if we have a clock, while the clock is high, the data must be stable. So what you must do, whether it's the master or the slave transmitting, doesn't matter which one it is, if that's the clock and that's the serial data, for the whole of the duration of the high part of the clock, the data line must be either always a 1 or always a 0. Remember, with SPI, you actually had the change of state triggered it. But with I2C, it says while the clock is high, that must now be stable. And what you can do then, therefore, is while it's low, you can change the state, but when the clock goes high, it must have stabilized out. So the whole of the high period of the clock, it must be at a stable state. That is essential. So what we have is we've now defined the ability to transmit a logic 0 and a logic 1. There's our clock. a logic level 1 would mean undetermined, but for the whole of the duration of the clock pulse, that must be at a logic level 1 state. So that is a 1. And for a 0, for the same clock period, we don't care what it is before, but just before the clock goes high, it must go low, it must stay low for after the clock period, and now that will be a logic level 0. So for the whole of the clock period, if you're high, that's a 1, or if for the whole of the clock period you're low, that is a 0. Those are the rules. While the clock is high, the data line must be stable for the whole of that clock period, all of it. If you want to change the data, you take the clock line low, and then you can fiddle around with the data line. It's outputting a 0 or 1, but then it must stabilize, and then you take the clock high and hold it high while the other end reads it in. Those are the rules. 2 bits as logic level 0 and a logic level 1. But there are 2 other types of bits that are defined by the system, and these are used for delimiting the frames. That is achieved by violating the rule I've just told you. And what they have defined is a thing called a start bit, a starter frame. The way that works is that if our clock line is high and there is a transition on the data line, so there's the clock and there's the data, we violate our rule by deliberately changing the state of our data line in the middle of the clock, going from a high to a low. That means that is the start of frame delimiter. And the opposite of that is that if during the clock sequence we go from low to high, there's the clock, there's the data, that is defined as a stop. So what we do is we use the start and the stop signals to start a transmission and to end it. And that means we have clearly delimited the whole of the transfer of the frames between the master and the slave, and once we've stopped the transmission, everything can resynchronize cleanly on the next start transmission. So a typical transmission. Let's get away from the bits now. You've seen how the bits are done. You've seen how a logic level 0 is done, a logic level 1, a start bit and a stop bit. I'll just refer to them now as start, stop, 1 and 0. So a typical transmission would consist of the line is idling, does anything we like, we don't know what it is. You would get a start, then you would output bits forward and back in some controlled manner. I'll look at how that's done in a minute. Finally, the master outputs a stop, and that is the end of transmission. So here is the whole transmission period that cleanly ends it, and then you can restart a new transmission. Let's look at the structure of what happens in here. As with SPI, all data is transferred in bytes, 8 bits at a time, most significant bit first, bit 7 down to bit 0. Whenever a byte is transmitted, regardless of whether it's sent out by the master or by the slave, the receiver always acknowledges receipt of that byte. And it does that by outputting a logic level 0. Why is that? Why a 0? Well, all transmission lines, when they're off or idling, are always at logic level 1. Whatever standard you look at, you always have an idle line is at logic level 1. How else would you know it's powered up and the link is there? The basic telegraph's key, when the power is wired up, the line is active, and it's the pressing of the telegraph key breaks that and makes a logic level 0. All transmission lines, RS-232, Ethernet, wide area network structures, an idling line is always at a logic level 1. It's pulling it to a 0 that indicates I am on and active. So how do we transmit our data? Well, in time sequence, first thing we would do is that we would output a start bit, Then the master will output an 8-bit command. So that's going master to slave. There's our master. Let's start that drawing again. It's not very neat. Start. There's our master. There's our slave. The start bit is transmitted by the master to the slave. It then follows it up with its first command. And that master to slave is always 8 bits long. The start bit's only 1 bit long. Remember, it's a funny bit, but it is still 1 bit long. The slave, once it's clocked in those 8 bits, it then replies by sending a 0 back to say, I have now received the data. I have now received the data. That is the acknowledgement. So, what happens next? What do we do? What happens next? Well, this is always determined by the contents of the least significant bit. It could be a 0 or a 1. That bit tells the system, tells the receiver, whether or not the next operation is a read or a write operation. If it was a write operation, then the next thing that would happen is that another command would go off in that direction. So a second command is instructed by the fact that there was a write, a logic level 0, in the least significant bit of the last byte that was written. So really that's telling us what happens next. So let's look in detail again at a write operation. The write operation, whatever it is, there will always be a start, a command, 8 bits long, and the last bit will be a 0. That goes out, master to slave. The slave acknowledges by transmitting back just 1 bit, a 0. And now what will follow is the next command will then follow on master slave, because it's that bit, the least significant bit, tells us whether the next transfer will be master to slave or slave to master. So that's how that's done. What about a read operation? Well, with a read operation, we have start, as before. That goes master slave, then we get a command master slave, but this time the read write bit is set to a 1. That means the next operation is a read from the slave back to the master. What happens? Well, first the slave acknowledges receipt of that command as before. Every byte transfer, there must always be an acknowledgement bit that comes back. But now the next operation will be a transfer of 8 bits from the slave back to the master. And again, the slave would say 1 or 0, depending on whether it wants to now send another byte of data or not. The state of this bit determines the direction of the next operation. Because the slave has now transmitted 8 bits, it's the master's turn to acknowledge what has happened. And so this can continue with a byte followed by an acknowledgement, byte by acknowledgement, with the direction determined by the least significant bit, and finally everything is closed down by the issuing of a stop bit, a single stop bit. Now that's a lot to take in, but it is all in the book. and you should be able to read it up. And it is normal practice, it's your job, the programmer, to write the I2C routines. So let's run through I2C. Inter-integrated circuit. 2 wires, half duplex. 1 wire is the clock, the other wire is the data. Data can travel from master to slave or slave to master. We've defined 4 bits. They're in the book. A start bit, a stop bit, a 1 and a 0. That's all you need to set up the link. All transactions are packaged between a start bit and a stop bit. All data transfers are done in bytes. There's always 8 bits. Every time a byte is transmitted, whoever is receiving it must acknowledge that by sending back a logic level 0. The least significant bit of each transfer is the data direction bit. It tells us what the next transfer's direction is going to be. So by using this structure, we can bounce information backwards and forwards between the peripheral devices and our master system in a half duplex manner, closing everything down at the end by issuing a stop bit at the end of the transaction. So we've discussed the 3-wire techniques, SPI, the 2-wire techniques, I2C, but the really interesting new developments, recent developments, are the 1-wire devices. Now I've got an example here. This particular card, this is in fact the circuit card from a tachograph in a lorry, and it's used to monitor the whole of the driving situation over a 24-hour period. And what is required is that the driver carries one of these things, a small button memory. Put it down there. A small button memory. Now this device, it looks like a battery because that's what it is. What it actually is, it's a battery-backed RAM. We've got in these devices a standard battery cell, looks like any normal battery, and also you have in these devices memory. And you come in various sizes. They're now available in 64K bit memory sizes, and they are growing because all they've done is they've been packaged into a standard battery cell and memory location as well. And what happens on this card is that the data is stored into this battery-backed memory here, and that's just kept alive by an onboard battery, but we have to suck it out of this card, which is embedded somewhere in the vehicle. And the way you do that is you come along with your button memory and you connect it to the single wire tap point, and once it's on there, data now is transferred over the single wire connection from the onboard memory to our battery memory. And when we've done the transfer, we can take the battery away and we go back to our base, back at the office, and we use a device such as this, which they call a wand. One end of it, that's actually an RS-232 port. We plug it into the back of our PC. We take our memory, we take our wand, we touch it on. That's why they're called touch memories. That sucks out all the data from the button memory into the computer, and then we can process it using some nice Windows Flash program. You can write the Windows programs. I'll stick with writing these programs because I think these are more fun. How does the touch memory system work? It's a single wire connection. That's the clever thing about it. How does it do it? Well, it combines onto a single wire both the clock and the data. Similar way to Manchester encoding on Ethernet, which combines the clock and data onto a single system to give you synchronous links. So the button memory also combines it onto a single wire. And the way it defines it, again this is in your notes, section 4.3. When the button is connected, we have the line is normally idling at a logic level 1, as all transmission links should do. Our master, which is our computer, pulls it low for a clock period, and then for an equal period of time, that is when we output either a 1 or a 0. So if we wish to output a logic level 1, we would go clock 1. And if you wanted to output a logic level 0, we'd say, here's the clock, and here's the logic level 0. So there's a 1, and there is a 0. So we have a mechanism to output 1s and 0s. That is done simply by clocking from our computer logic level 1s and logic level 0s into the memory. There's a small processor in here as well, which I forgot to mention. How does data get back? Well, as with the other two standards, the bits are combined together into bytes. If we have the ability to transmit 1s and 0s over the physical layer, we can now build up a complete ISO 7-layer model for data transmission between these devices and external touch memory probes. And that standard is published and is freely available for anybody to use. And the way it works is that we have logic level 1s, logic level 0s, and these are grouped together into 8-bit commands. 8 bits. So there are 8-bit commands are clocked out. Unlike the other standards, it's least significant bit first. But I don't need you to go into that sort of detail. If ever you need to get involved in touch memories, there are plenty of libraries available on the web or from the manufacturers of how to do it. They'll give you the software. They want to sell you the components, so they actually give you the software to drive it. So it's actually quite a nice standard to go for. 8-bit commands, bytes, and then if the command is a read operation, all that happens is if we were trying to read, the master would output a clock signal, and then it would read back in a 1 or a 0 from the slave device. So it outputs a clock and then reverses the half duplex line, and it reads back in the state of the line. So we have here a simple mechanism, single wire, half duplex operation. We combine the clock with the data, we can burst out 8 bits of data, and we can read back 8 bits of data. But remember, it's always the master device that outputs the clock. So let's have a resume. We've gone through 3 different serial comm standards. Why have we done it? We've done it to get away from these horrendously big boards that use, well, here's a worse, but this is an incredibly large bus, and we've got so many components on here. We've had to bring the bus all around the processor, lots of wires everywhere, and the camera is even homing in on the errors I made in the circuit, which you shouldn't tell anybody else about, but they're the small minor repairs. And we have a bus structure, and this is the problem with bus. As soon as you make it more complex, you start making mistakes which you have to rectify. Big boards, more things to go wrong, cost more to manufacture. We want to get away from these structures, and we do that by using these serial communication techniques that link together ICs on the board using single tracks. And we've looked at 3 different mechanisms. It's SPI, 3-wire full duplex. I2C, 2-wire half duplex, and the touch memory or single wire standards, 1 wire, which also is a half duplex standard, but it combines the clock and the data onto the single wire. What are the rules about it? SPI, remember, there's a data line, data in, data out, and clock. All the bits are transferred as bytes, and data has to be valid on the falling edge. Also remember, with SPI, everything's out of phase. Output a command, and on the next read back you get the result from the previous command. Most significant bit first. But there's no framing, and it's half duplex and there's redundancy, so why bother? So instead, the far more robust I2C inter-integrated circuit standard came into being. 2 wires, half duplex, with a clock and a data line. And remember, we defined a 1, a 0, a start and a stop. And that start and stop bit gave us the ability to frame our transactions, to resynchronize the bytes. And every byte transfer, whatever the direction it went in, was followed by an acknowledgement. You always had an acknowledgement. The last bit, the least significant bit, told us whether the next transfer was forward or back. And the most compact standard of all, the touch memory standard, one wire standard, combined the clock and the data together. Now, they were originally developed actually purely for these touch memories, so it's often called the touch memory standard. And the idea was that you could have these touch memory probes built into the board. You came along with the memory, you literally touch on. You might have seen these actually. I've seen these on a lot of vending machines these days. I've seen them in little casinos where you buy your chips on these little buttons, and you use that to play the fruit machines. But you touch that on, it sucks the data in and out, and then you take that data off to another station and you touch it on. Now, that mechanism was known as the touch memory standard, but because it is so efficient, there are now coming on the market a range of standard peripheral devices that don't have this ability to move around, but just use the touch memory concept to do a single wire transfer between chips on a single board. So everything we've spoken about in this lecture has all been to do with how chips on board transfer data between each other. And by using these single, dual or triple wire techniques, you can get very, very compact circuits, because let's face it, the bulk of the circuitry, the bulk of the board, isn't taken up with components, it's taken up with the tracks. And the fewer tracks you get, the more compact the electronics can be, the smaller and smaller can be our final end microcontrollers. Hello, welcome back. So we've now discussed input devices, output devices, how devices talk to each other on printed circuit boards, either by parallel architectures and also by serial architectures. Something else we now need to consider is how do boards talk to other boards over distances? And the clear answer is to use some form of local area network, LAN technology. Now, most of the LAN technologies you might have heard of in the past, Ethernet, token rings, etc., they've been developed for transferring large amounts of data between users and peripheral devices, or from users into the web. They're not really suitable for use in process plant and instrumentation. Instead, there have grown up independently in process industries a whole family of local area network strategies which are suited more towards sending small packets of information between distributed devices. Why small? Because we're not talking about file transfers or images. We're usually talking about very, very small amounts of data. Take a car. You look inside any modern vehicle today, you will not find a wiring harness in it. All cars of all major manufacturers have, for about the last 5 to 10 years, 10 years for the real expensive cars, but even ordinary modest cars, 4 to 5 years, all cars are now fitted with local area networks. You don't get the horrible wiring harnesses you used to get. If you don't believe me, find a nice new car, preferably an expensive one, lift it up the bonnet, look inside. You will not see wires everywhere. You will see instead a distributed local area network within that car, and what you will have somewhere is a central processor, usually the engine management unit. You will have at the front of the vehicle a front end module that's controlling the lights and other sensors. You'll have a rear end module controlling the electrics at the rear, the fuel pump. Somewhere or other around about the wheels, you'll have an ABS unit for the braking and the road speed sensor. And there'll be a host of other bits of electronics around. There will be somewhere the fuel injection system, And all of these devices will be, instead of being wired together with lots and lots of wires, will in fact be connected on a LAN, a local area network, in your own car. In fact, I've got a project coming in the next few weeks where we haven't got just one LAN, we have two LANs in the same car, and we're having to develop a bridge to bridge the high-speed data from the engine management system to the low-speed LAN that's being used to drive the instrument cluster in front of the driver. So LAN technology is here and now and is in everyday use. You'll find LANs in washing machines now, believe it or not. We've just developed a very small LAN to go into a gas cooker. Why? Because it means you can have fewer wires. And as I've said before, wires cost money and maintenance. The fewer wires you have, the better. So in process industries, there has been developed over the many years a whole family of LANs, generally known as field bus technology. Field bus. Every manufacturer has come out with their own standard for it, and they have been sitting on an international standards body for over 15 years trying to agree a common standard. And the trouble is because it's full of manufacturers and not users, they haven't agreed. And the end result is that the market is flooded with different implementations. So you'll find things called Modbus or Profibus or Field Bus. This bus, that bus, every manufacturer has brought out their own. Because they're fighting for supremacy, the end users, in fact, have now overcome this by declaring their own standard. And that standard is coming to the top of the pile, and that is a very important structure, and it's called CAN bus. CAN bus stands for Control Area Network. Control Area Network. And the reason it has become, in fact, it was developed, I have to be fair, it was developed by a conglomerate including mainly Bosch, who pushed it, and a few other major players were in it. But unlike all the other manufacturers, they published the standard and they said, please use it. And the automotive industry has standardized upon this and selected it as the main standard for use in vehicle wiring harnesses. So all the major players in vehicle manufacture have used CAN bus. Car manufacturers are a major part of the economy, and because they've standardized on it, you've ended up with a major group of users forcing the pace and forcing all these manufacturers to move towards that standard. So even though you'll still see the other types of bus around, you'll notice more and more that they're dual compatibility. So you'll have a particular instrument manufacturer will still have their preferred standard, a so-called standard, but also it will support CAN bus. So I'm only going to talk to you about Control Area Network bus today, because there is no doubt that is the one that will be finally selected as the international standard for wiring up vehicles and for factories and processes. Now, how does CAN bus work? Now, unlike any other network you may have come across, there is no such concept as an end-to-end link. That's the main difference with CAN bus over other networks, traditional data networks. With a wide area network, be it a virtual circuit or a datagram, or be it a LAN circuit with a token ring or Ethernet, it's always a block of data going from one user to another. There is always this concept of the link. So let's assume we have a network and we've got loads of users on this network, be it a bus structure, it could be true for a ring or for a mesh structure. Every user has an address with a traditional LAN, and whenever a message is output onto the network, it's always routed to a particular user. So the role of the network is merely to act as the carrier, taking the data from one user over the network into another user. There is always the concept of a link. You don't have that with CAN bus. The requirement was totally different, and it's for that reason none of the traditional known LAN structures were chosen by the automotive industry or process control people. The reason being is they don't recognize this concept of an end-to-end link. If there is some information about the factory, many different parts of the network may be interested in it. You never have the concept of a particular transmitter and a particular receiver. So for example, if it was a factory, a steel plant, let us say, and there is a sensor that is sensing the temperature of the molten ore, it broadcasts that onto the network. There are many other users that are interested in it. There's the actual temperature controller itself trying to maintain that temperature. There will be an information panel somewhere in the control network where you need to display the temperature. So there are always many users who want to view one piece of information. So we don't have the idea of an address structure. We do not say, here's user A, here's user B, and messages go from A to B. Instead, all messages are broadcast to everybody in the network, and anybody who's interested in that information is allowed to tune into it. It's more like the television, a broadcast structure, and because it's a broadcast structure, it also has to use a broadcast type topology. So all CAN bus networks are always either a bus or a star. So let's just remind ourselves, what is a bus? A bus is where you have a single high-speed cable and all the nodes sit on that. Alternatively, it can be a star arrangement with a single point going to many nodes coming back to a single central link. And in fact, most CAN bus LANs combine stars with buses. The key thing is that whenever a single, let's assume we're broadcasting here, when that message is broadcast out onto the cable, everybody receives that information. Because it is a single wire, whether it's as a bus or as a star arrangement in a hub or however you do it, whenever a single node transmits information, everybody gets it. And that means if you're interested in it, you can listen to it. So we don't have the idea of a point-to-point link. We don't have a sender or a receiver with any of the field bus standards. Instead, we have this idea of broadcast channels, just like television. And a broadcast channel is an entity that exists in the network. It defines a particular block of information that is broadcast onto the network. So what we have, instead of point-to-point links, let's just go to our simple CAN bus system. We have what are known as channels. Channels of information, where a channel isn't a routing. So we have a broadcast media, and here we have the CAN bus cabling, and we have channels. A channel is an entity that exists within the network itself, an information block, shall we say. And that means that somewhere one of the nodes must be broadcasting that information. Whatever that information is, something must be the source of it. But every single node, or only those that are interested, are allowed to listen to it. So a channel is an entity that exists on the bus itself. So how does it work? Now let's go back to our picture. Each of our nodes can both broadcast and receive. Any node can typically broadcast up to 16 channels. So every one of these can broadcast 16 channels. That's a typical system. There are others that do more, some do less, but typically every node is capable of broadcasting 16 channels. And these are blocks of information that exist, are broadcast from time to time onto the bus, and anybody who's interested in them, they read it. So it's just like having television or radio, an aerial, that broadcasts to everybody, and only if you're interested in it do you listen to it. Each node on the network can broadcast up to 16 channels. That's a typical system. And each node can receive up to 16 channels. So think of our car. Our car, one of the most important bits of information is how fast are we going. It's usually the ABS, the braking system, that does that, because the braking system is in the wheel and it is monitoring the rotation of the car wheel at all times. So it's the ABS unit in modern vehicles that has the job of broadcasting the road speed information channel. Who's interested in that? The fuel injection system. It tunes into that channel and listens to it. The driver's information panel, because you've got the speedo dial, that tunes into that channel and listens to it. The fuel pump tunes in and listens to it, because the faster you're going, the more fuel it pumps. So we have this idea. A single node, the ABS unit, broadcasts the road speed information. Everybody who's interested in that simply tunes into it, and remember, they've got 16 channels. They can listen to 16 channels simultaneously. They gobble that data up. So that's CAN bus. How's it done? Let's look at the structure of a CAN bus frame. The first 2 bytes of the CAN bus frame contain the channel address. Now the address can be up to 11 bits long. 11 bits, so you've got what, 2048 different addresses there. That's enormous. That is a large amount of memory. You don't need that. Most systems might use 20 or 30 channels, so 11 bits is total overkill. Quite honestly, you just don't need that much. But the channels can be defined with an 11-bit address. Now on the first byte of the data, that's got 8 bits of it. That's the most significant bits. And then the next 3 bits, you get the 3 least significant bits in the next byte, where that's bit 7 to 0, bit 7 to bit 0. So there are our 11-bit address comes first. The next bit there is called the response bit. I'm not going to go into what that does. And then we get a length. 4 bits for the length. Now what that field is for is to tell us how much data follows. And as I've said, the whole purpose of CAN bus is to pack it up to small bits of information. The maximum amount of data you are allowed to transmit is 8 bytes of data. It's not very big, but that's usually more than adequate for most real-time systems. Quite honestly, long packets will take too long to transmit. So the way this works is that the length bit, that is a number from 0 to 8. Anything greater than 8 is illegal, and that tells us how many data packets, bytes, now follow that particular channel header. So the overall structure is you get 8 bits, 3 bits, the response byte, and then you get 4 bits there. Those first 11 bits, that is the channel address, and then you get 4 bits, which is the length, and then you will get that number of bytes will follow on up to a maximum of 8. And that is the whole structure of a CAN bus frame. It's extremely simple. And what's nice, because it is so popular, there are a large number of devices available off the shelf that do this for you. You can even buy microcontrollers from people like Philips and Siemens, and there are equivalents made by other manufacturers that actually have CAN bus interfaces built into the microcontroller. A few years ago you used to get serial comms as standard in these devices. They don't bother with that anymore. Now you get as standard CAN bus interfaces, I2C interfaces, all integrated into the single device so that you can have these structures. So let's just have a review of what CAN bus is all about. Why do you have local area networks? Because you want to reduce the wiring. And the neatest way to do that is to use LAN technology. But the LAN technology we require for process plant is different to that has grown up for the data communications industry. We want to transfer small bits of information, not large files or pictures or graphics, and we don't want to send it point to point. We need to broadcast our message to everybody who wants to know about it. So the industry has generally standardized around CAN bus, the Control Area Network standard, and instead of defining point-to-point links, it defines channels, where a channel is an information entity on the bus. Each node can transmit, broadcast up to 16 channels, and each node can receive up to 16 channels. The address of a channel is stored in 11 bits, which is more than enough, and you can transmit up to 8 data bytes after each address header. So the format for a CAN bus message consists of the first 2 bytes is the header with 8 bits, and 3 bits gives us our 11-bit channel address, a response bit which I have not described to you, and then we get the length bits, 4 bits in all, and that can take the value 0 to 8. So up to 8 data bytes could be transmitted, which then just follow on the CAN bus message. Why 0? Well, you may not have any information to send. You may define that CAN bus address 37E, if it exists on the bus, means that's emergency stop, shut everything down. So the message itself, the very fact the channel is broadcasting, could just be the message in its own right. There may not be any data. So CAN bus is a very popular facility used to link together different systems, nodes around a factory or a car or a vehicle. So let's have a very brief demonstration of how CAN bus works. Now what I've said is that a message, a channel, is merely some information. It's only bits. But what do they mean? They can mean different things to both the sender and the receiver. Let's go to my simple demonstration here. Here we have two CAN bus cards. These are general purpose cards used in factories. Here we have a processor and we have some input devices. On this side here, these are switched inputs. When we connect switches across these two poles, we can detect a switch closure or switch opening. And here, just for some simulation, these are actually high current outputs, but I've put a light emitting diode onto them so that we can actually see the switches closing. So if I was to close, for example, a switch by simply shorting things out, hopefully you can see the lights are coming on. Now how is that achieved? Because these are two totally independent boards. It's done via this two-wire CAN bus network, totally independent boards. Because what I've done is I've defined a CAN bus channel where this is transmitting the channel, and what it's transmitting is the status of these switches. So I've got these switches being broadcast on a regular basis into the CAN bus network, which is just two flimsy little wires. That's all they are. And this unit has been tuned to receive that channel off of this board. And what I've done is I've mapped that data to these outputs. So what I'm showing here is a switch closure on this board is being used to enable an actuator. This is a high voltage output on the second board, which is connected only by the wires. So here we come in onto board 1, close the switch, and then we see it's actuated by the LED coming on. And we've achieved that by creating an information channel where the broadcaster is broadcasting its switches in that channel, the receiver, it's mapping those switches to its outputs, and so we don't actually define the functionality of the data. The information is there in the channel for you to do as you wish, and we can do the same thing the other direction, because there is another information channel that has been defined as these switches, and hopefully if all is still working, we should see this LED is coming on, because what I've defined is that channel there has been mapped to this output state there, and that switch there has been connected to that switch there. So over the CAN bus network, which is just the two-wire connection, we are able to transfer real data between hardwired switches. There's the switches on one card being broadcast on the channel, turning on the actuators. These could be motors, drills, machines, whatever it is at the other end, and that is switching on this unit here. This card, actually, these cards are a family of devices that my company manufactures. It's been used in a wide range of applications. It's been used for robotics. They're currently being used in the new X-ray scanners going into airports around Britain. A general purpose tool, and the reason we can link them together is because of the CAN bus technology.